你有这么冷？你就是很看动的。那他写到就不冷了。没洗，我等我有钱我就会洗，我买不起。我说利用户，我有什么去买？黑五的，黑五的，本来我是德国比较多。
Okay, let's get started. Just to recap on last week, so we found in the lecture there are more small particles in the cloud than large particles, this exponential distribution, and it depends on two parameters, the slope and the intercept, where it crosses the y-axis at x equals 0 is the intercept, and the slope on a log linear scale is the slope of the exponential distribution. And we talked about moments of the distribution. So this is multiply by diameter, integrate from 0 to infinity. Turns out to be quite useful for weather forecasting because the moments of a particle size distribution are used to calculate the processes in a cloud scheme. One being the first moment. So the first moment is related to how fast the cloud droplets grow from water vapour. The second moment is related to the radiative properties, how much radiation is reflected away. I didn't talk about the precipitation rate, but it turns out the precipitation rate, I'll talk about it later, is related to the fifth moment. So all these moments are useful in the cloud scheme. They're used in the cloud scheme in a weather forecast model or a climate model to predict these useful parameters. And then we talked about geoengineering, and the thing we considered about geoengineering is under what conditions might it be useful, and it turns out that it's only most effective in conditions when you already have low aerosol particle concentrations. And this is because if you think about the thin clouds where this geoengineering scheme has been proposed, the marine cloud wrapping geoengineering scheme, the thin clouds, for a given liquid water content, cloud water content in the cloud, the radiative properties of the cloud, M2, goes as the zeroth moment, so that's the number of cloud droplets, to the power 1/3. So what does that mean? That means if you start with low cloud droplet numbers, then you can change the radiative property quite a lot by changing the number by just a little bit. As this curve goes, it has a large gradient at first and then the gradient levels off. Whereas if M0, the number of cloud drops, is already large, then you can't change the radiative properties of the cloud by very much. And Kelvin's effect also comes into this because the size of the aerosol particles you inject in geoengineering is also important. So today I'm going to talk about ice. We'll be talking about liquid particles now for a while, and I want to talk about ice particles. What temperature does liquid water freeze at? I know at least one person in the audience has worked on this over the summer. So what temperature do you think liquid water freezes at? That's some liquid water. -37. Someone's done their homework. Pure liquid water doesn't freeze until the temperature gets to about -37, -38. Okay? So physicists, I guess, you'll have looked at your phase diagrams and you'll have seen liquid water, and the boundary between liquid water and ice water is 273 Kelvin, 0 degrees Celsius. That's at equilibrium. Now nucleation, ice nucleation is not an equilibrium process. And in the atmosphere, because water is being deposited onto the aerosol particles from the vapour, directly from the vapour, we can have really pure cloud droplets. And in pure liquid water doesn't freeze until the temperature gets to -37, -38 or so. Okay. But we do see ice clouds in the atmosphere at temperatures warmer than that. And so we'll talk today about how that happens. So I just want to show you, I couldn't do the experiment today in the lecture theatre, but I have on the web page a little experiment here that I did in the lab, which is ice nucleation in supercooled water. So you can have a look at this in your own time, but we'll just look at part of it today. It's only about 30 seconds to a minute long. So this is a water cooler. The temperature of the water cooler is -5, and there's a bottle of liquid water inside. It's actually mineral water. So that mineral water is supercooled to -5. Obviously it's not pure water. And you can see it's liquid. Well, maybe you can see it's liquid. And I've just tapped the bottle there, and what you'll see is the liquid water inside start to freeze. You see that? So you see the ice front coming down. So ice has been nucleated now in that bottle, and the ice is just crystallising through that bottle. And it doesn't happen instantaneously. That's because latent heat needs to be radiated away for the temperature to be 0 degrees Celsius on the ice. So how does that happen? Well, that happens. That actually doesn't happen in the atmosphere. That's the cavitation effect. What's happening in that case is the liquid water. When I tap the liquid water, small bubbles are forming at the surface of the liquid water, and then those bubbles are escaping, and that's causing an adiabatic expansion of the air inside, which cools the air to temperatures lower than -37, very locally, and that's where we see the nucleation at the top of the liquid water. Now in this case, I'm just going to show that supercooled water, when it comes into contact with a metal surface that has some impurities on the metal surface, is going to freeze. So you can start to see some slush coming out of the bottle. It's not all freezing, because there's a significant amount of latent heat that also needs to be released. But you can see, hopefully you can see there's some ice on the bottom of that pan there. Okay, so maybe we learned something. So supercooled water doesn't necessarily freeze at 0 degrees Celsius, which is interesting. It turns out to be important. Why is it important? Who wants to have a guess at what's happening in this cloud here? So this is looking up at the sky at a stratocumulus cloud. These areas here are stratocumulus clouds, or even altostratus clouds. They're very thin layer clouds. What do you think's happening in that picture? Anyone want to guess?
Downburst.
Say again.
Downburst.
Downburst. Oh, okay. So you're thinking about some kind of downdraft.
Yeah.
It's not actually, but good guess. Good guess. So it's related to ice nucleation. So if you're lucky near airports, you'll see this effect. You'll see this effect near an airport where you have these altostratus clouds. Altostratus clouds tend to be supercooled liquid layers, very thin supercooled liquid layers. They look almost like a stratocumulus cloud, but they're a little bit colder. Okay, and they're an important cloud type, quite common. Now what's happened here, close to the airport, is an aeroplane that's flew through this cloud layer, and as the plane flies through the cloud layer, air travels over the wings, and as it comes off the wings, it causes an adiabatic expansion, okay, which allows the air over the wings to supercool to temperatures below -37. And then ice nucleates in this cloud layer. And what happens is quite interesting, and we'll learn more about it. So what's happened in this case is, okay, so we've got the supercooled liquid cloud layer, which is not raining, it's not precipitating, it's just staying there, quite stable. Once we nucleate ice in the layer, then the ice particles start to grow and the droplets evaporate. And that's because ice is the stable phase at those temperatures. So ice grows at the expense of the liquid droplets. And we'll learn more about that process tomorrow in tomorrow's lecture. There's a name for it, the Bergevin-Dyson process, which we'll learn. But because the ice particles grow, and they're the stable phase, they grow to sizes much larger than the droplets. And because of that, they're able to fall out of the cloud. So this is actually a fall streak. It's actually snow forming in this cloud layer and starting to precipitate out of the cloud layer. And so you can notice that, you can actually see the precipitation falling out of the cloud, and there's also an effect on the radiative properties of the cloud, an important radiative effect. So more sunlight's getting through. So this cloud layer cannot reflect as much solar radiation back to space. So ice in clouds has these important effects. So going back to our simplified clouds over the ocean, so we had clouds, we increased aerosol particles. If the clouds are supercooled, well, first of all, if we increase aerosol particles and they're not ice nuclei, then the amount of radiation that gets reflected back to space increases as we increase the number of cloud drops. But if we add some ice nuclei and the temperature is low enough, then the ice particles grow to larger sizes, but radiatively the cloud cannot reflect as much radiation back to space. Okay, so that's an important effect on the albedo. And precipitation wise, so this next slide is an animation of some radar data. So this is a weather radar probing the vertical structure of a cloud. So it's vertical against distance. And this is the radar facility at Chilbolton. So it's a 3 gigahertz radar, which is able to look at the precipitation in a cloud. So the echoes that you get back from clouds using this radar are sensitive to precipitation sized particles. So fairly large sized particles. So it shows you the radar reflectivity, and what's happening is we have ice, and the ice approaches the melting level here and melts and falls as rain. So you can see the change in this gradient here as the rain starts to fall out of the cloud. You also see this effect known as the bright band. So that bright band is known to be due to an effect when the ice particles consist of both ice and they have liquid on the surface. You get this bright band effect. So that's the signature of melting ice crystals. And Benjamin Franklin, obviously all those years ago, originally wrote, much of what is rain when it arrives at the surface of Earth might have been snow where it began its descent. So that's an important effect there. So the numbers are for the mid-latitudes, where we live in the mid-latitudes, typically about 70% of precipitation on the ground starts its life as an ice crystal. And globally those numbers are more like 50-50. So in the tropics you get more warm rain, you get more rain that's initiated from the warm phase. Whereas in the mid-latitudes the numbers shift more towards the ice phase. So most rain in the mid-latitudes, where we are, starts its life as an ice crystal. Okay, so we've got these two effects. We've got the effect, the radiative effect on the cloud, and we've got the effect that ice crystals have on precipitation. So you might imagine for weather forecast models, we need to be able to describe how ice particles form in clouds, because not all cloud droplets will freeze. It depends on the kind of ice nucleating particles, special particles that are called ice nucleating particles in clouds. And this is a very active area of research. So what's actually happening first? Let's just go through some basic theory of what is happening during the nucleation process. So we've got liquid water. It's a disordered network of hydrogen bonds. Okay, so what does that mean? Every now and then we've got this big collection of water molecules, H2O, and every now and then the hydrogen molecules, the water molecules interact via hydrogen bonds. And that's a transient process. So the interaction might occur between these two molecules and then might occur between these two molecules. But that's kind of constantly in motion. So what do we mean by ice? So in order to form ice, first of all, ice, hexagonal ice, there's different forms of ice, but the important form of ice in the atmosphere is hexagonal ice. Now hexagonal ice is, you might imagine, a hexagonally ordered network of hydrogen bonds. Okay, and the average motion of water molecules in this ice structure indicates that the water molecules must slow down. Okay, so if we go to the disordered network of hydrogen bonds, liquid water, to ice, we make that transition. One thing that must happen is the average motion of the molecules, the H2O molecules, must slow down. And that releases heat. That's the latent heat of fusion that we've been talking about. That's the latent heat, that's the heat that's released as we form this ice structure. Okay, and now I'm going to talk about, first of all, how ice forms without the presence of an ice nucleus. So someone said down here, ice forms at -37 or so. So let's think about what happens when pure water freezes at -37. So this is known as the homogeneous nucleation of ice in supercooled water, and this is an important process in the atmosphere too if the temperature is low enough. So let's think about it. Got these points. It takes energy to form a surface of ice. The larger the surface, so this hexagonal ice, the larger the surface, the larger the energy required, and that's known as interfacial energy. I think the physicists may have come across this before in thermodynamics. No? Okay. So, before I get on to some analogies, I want to talk about the other form of energy. Energy is reduced by an increase in the volume of this ice surface. We'll call it an ice germ. So it's a really small particle of ice inside liquid water. And this is because the liquid molecules must slow down. That's latent heat gets released, and that scales with the volume of the ice. And so we need to do positive work to speed them up again. So we can add these two effects together. We've got surface energy and we've got volume energy. and that's the Gibbs free energy. Have you heard about that before? So add those two factors together. So the interfacial energy goes up as if you think about a spherical germ of ice, it goes up as R squared, and the volume energy comes down as R cubed. Add these two effects together, at some point there'll be a point where the Gibbs free energy is a maximum. Okay, if we can get over this barrier, and that's the point where ice is nucleated. So let's think about this balloon on a tap analogy. So I have a tap, I have a water balloon on the tap, I turn the tap on, water goes into the balloon. Okay, if I turn the tap on a little bit, the balloon will inflate and then it'll stop because the surface tension of the balloon is high enough to stop any more water entering the balloon. Have you come across this before? You turn the balloon on just a little bit. Same when you put air into a balloon, you start to blow the balloon up. You don't blow hard enough, it'll inflate to the point where the surface tension is high enough for no more air to go in. And then at some point, turn the tap on a little bit more, and it becomes a lot easier. Once you get over this surface energy barrier, it becomes a lot easier to put more water into the balloon. So at that point, the balloon's nucleated, the water balloon's nucleated. Okay? It's the same kind of effect here. We're talking about the sum of two energy terms. We've got the surface term, scaled as R squared, we've got the volume term, scaled as R cubed. Get over this maximum, that's the point of nucleation. So the point of this maximum here, the radius of this maxima, that's known as the critical radius for nucleation. The critical radius for an ice germ, or whatever you want to call it, something like that. So the key point, the larger the volume of liquid water, and the lower the temperature actually, the more likely an ice germ will be able to form. So why is this? Okay, so the lower the temperature, the less thermal energy there is. So it's easier to slow those water molecules down. And it just so happens that this does not happen in pure water. So I said minus 35, it's probably more like minus 37, minus 38 actually. But a lot of the atmosphere is in this temperature regime between 0 and minus 35. So we also need to consider that regime too. And that's the regime for heterogeneous ice nucleation. So we've got homogeneous ice nucleation. That's just pure water, no other substrate involved, no other particles involved. We can figure this out by considering the motion of liquid water molecules. Heterogeneous ice nucleation, we need to consider substrates. So we need to consider other particles that might interact with liquid water. And this is a fairly active research area being worked on. And there are different modes at which particles can nucleate ice. So these are known as freezing modes of heterogeneous ice nuclei or ice nucleating particles. You'll see IN or INP for ice nucleating particles. So the first one, deposition. This is where you have a solid particle usually, and then you can form ice when water goes directly from the vapor phase to the solid phase. Heterogeneous deposition, that's called. And then these two phases, these two pathways here are quite similar, so I've drawn a line around them. We have immersion freezing and condensation freezing. So immersion freezing, if you have a liquid droplet with some solid nuclei inside, and then you cool that liquid droplet to a temperature where the solid nuclei can act as an ice nucleus. Freezes, you form an ice crystal. So here we're considering interactions between the substrate and the vapor phase. Here we're considering interactions between the substrate and the liquid phase. There's a difference there. So we make a distinction between those two processes. So another process, condensation freezing. So this is where I always struggle with the difference between these two. So we have a solid nucleus. The droplet forms around this solid nucleus, and then at some temperature, heterogeneous nucleation happens between the liquid phase and the solid nucleus, and we get ice. I guess the main difference is that in condensation freezing, the same nucleus is acting as a cloud condensation nuclei. We know about cloud condensation nuclei. Whereas in immersion freezing, it may be that the solid nucleus enters the drop by some other form. So it could just be you have a raindrop, and the raindrop collides with the solid drop, with the solid nucleus, and then the nucleus finds itself inside the drop. Something like that. So there's a distinction between the two. And again, this is quite similar too, but it turns out you get very different efficiencies of nucleation. Contact nucleation. So you have a droplet and a solid nucleus, and then the solid nucleus contacts the droplet, that can cause ice particles to form. And you might think, well, that's quite similar to these two processes, because the solid nucleus is essentially interacting with the liquid phase, water, in the same way. It's an interaction between the surface of the solid nucleus and the liquid phase. But it turns out, for some unknown reason, we don't know why, it turns out that when this can happen, contact nucleation, the nucleation process is more efficient than the immersion freezing or condensation freezing process. So we've made this distinction between the two. But the other thing to bear in mind is that aerosol particles, or these solid nuclei, they can't really come into contact very easily with a droplet. And there are reasons for that. So for those reasons, the efficiency of solid nuclei colliding with droplets is quite low. For those reasons, we tend not to consider this one being as important as immersion or condensation freezing. Okay, and why is that? Okay, so there's two factors. You don't need to know this, but there's two factors for why contact nucleation is thought to be not as important in the atmosphere. And those factors are, if you have a cloud, then you usually have droplets that are growing from the vapour, and what that means is water molecules, we talked about this previous lectures, water molecules moving towards the droplets, okay? And those water molecules, that gradient in water vapour, can create a force, a diffusio-phoresis force, that's difficult to say, and that forces the aerosol particles towards the drop. But there's also another force, which is called thermophoresis, and that's as the molecules condense, latent heat's released, and so there's a temperature gradient between high temperature at the drop surface and low temperature further away, and that creates this force, this thermophoresis force, which forces the aerosol particles away. Now, thermophoresis wins out, basically, so that's the reason why contact nucleation is not as important. For immersion and condensation freezing, various measurements are showing that these are the important pathways. So these are the processes that we need to consider in the atmosphere. Kinds of particles that can act as ice nucleated particles, dust, so things like desert dust, mineral particles, biological particles. Biological particles, you can have really efficient ice nuclei, so at temperatures just below zero, things like pollen, viruses, other bacteria, they're good, and any others. So yes, soot particles they are ice nuclei, but tend not to be very efficient. But because there's so much soot emissions, they still might be an important source of atmospheric ice nuclei. Okay, so just a bit of background on ice nucleating particles. Now I want to talk about, we'll go through some of the theory in a little bit, but I want to talk about, if we're talking about heterogeneous ion and we're talking about immersion freezing, then there are two areas that you need to be aware of. And there are two ways of treating the nucleation process. These are two ways of treating the nucleation process from a theoretical point of view. So the first one's known as the stochastic hypothesis. So the reason why I'm talking about it, the reason why I'm giving you the background, is in the exam I may ask you to discuss the differences between homogeneous, heterogeneous and stochastic and singular hypothesis. So the first one's known as the stochastic hypothesis. So let's talk about what we mean by the stochastic hypothesis. Let's say we've got two aerosol particles. So these are aerosol particles, these are dust particles, say. One's at a high temperature and one's at a low temperature. And we keep the temperature constant. And these little specks on the aerosol particles, these are sites at which ice nucleation can happen. So if these aerosol particles are inside a liquid drop, these sites are the points at which the ice can be nucleated. And what happens is you only need one of these sites to be active for the droplet to freeze, because once ice nucleation's happened, crystallization takes place throughout the whole of the drop. So stochastic means we can keep these drops at the same temperature, and at some point, if we wait long enough, ice will be nucleated. You see, ice is nucleated at this point here, and we might expect it to nucleate at the colder temperature first, before the higher temperature, okay? So the longer we wait, the more chance we have of one of these ice nucleating sites to be active. If we were to repeat that experiment again, so the first time we did the experiment, this site became active. If we were to repeat the experiment again, we wouldn't necessarily observe that the same site will become active. So what we can do with the stochastic mechanism is quantify the average freezing rate. It's very similar to radioactive decay. You don't know which nuclei is going to decay, but you know the average decay rate in radioactive decay. So the equations are exactly the same as for radioactive decay. You get this exponential dependence on time. Make sense? I'll go through the equations in a minute. So the next thing you need to be aware of, so actually, the stochastic hypothesis, typically, it can do a good job in some situations, but typically it can predict freezing rates that are too high. So it over-predicts the amount of ice crystals we'll get in a cloud. So the other hypothesis is the singular hypothesis. So we've got different dust particles. We've got dust particles with ice nucleating sites on them. And what happens with the singular hypothesis is there's no dependence on time. It doesn't depend on time. It depends on temperature only, whether a particle nucleates ice. So we start at a high temperature, we cool down, and we might expect some of the sites to become active. The temperature at which those sites become active are well defined. It's a well defined temperature. Okay? And if we were to warm the particles up and repeat the experiment, we'd expect the same sites to become active. So you can see the difference between those two hypotheses. Okay? So very different ways of thinking about the nucleation process. Now, typically, we find that the singular hypothesis predicts freezing rates that are in very good agreement with data, which might be a bit of a surprise, but nevertheless that's what we find. And so that's what the modelling and weather forecast community have adopted. They've adopted this singular hypothesis to describe ice nucleation in numerical models. Okay, so that there's the singular hypothesis, there's the stochastic hypothesis. I would expect you to be able to discuss those two processes in an exam. So you'll be able to write about them and explain what they mean. Okay? So just make sure you can do that. Now to extend this a little bit further, if you want to quantify heterogeneous ice nuclei, then a common way of doing this in the literature now is a concept that's called the ice active surface site density. Bit of a mouthful. Ice active, so sites that are ice active, they're going to nucleate ice, and it's something to do with the surface site density. So the surface sites on an ice nucleus, and there's a density of surface sites. If we know what the density is of these ice active sites, then we've quantified the ice nucleation efficiency of a material. And this is known, this is given the symbol N subscript S, which is a function of temperature. It describes the number of ice nuclei per unit surface area on a particle. So if we think about a dust sample, desert dust sample say, then we can define this parameter NS, which is a function of temperature. And the product of NS and the surface area tells us how many ice nuclei are on that particular particle, if that makes sense. Yeah. So as you might expect, NS gets larger as the temperature decreases. So temperature goes down, we have more ice active sites. So you've got more chance of nucleating an ice particle for lower temperatures. And it's a singular theory. So NS is a well-defined function that depends on temperature. Okay. So I want to show you, I'll go through the details of that in just 1 minute, but I want to show you some experiments we've done looking at ice nucleation in Manchester. So over the road in my lab, we have this large cloud chamber, and what I'll probably do, so what we know, week 9 are we? So in week 11, for the last lecture in week 11, I'm happy to give a tour of the lab and show you these facilities. So we can do that. If anyone's interested, we can go walk around the lab and see, have a look at these facilities, and you can ask me questions about it if you like. But yeah, okay. So it's called the Manchester Ice Cloud Chamber. What is it? It's a fairly unique facility in the UK. There's only one of these in the UK. There's another cloud chamber in Germany who we collaborate with. There's one at CERN where we collaborate with CERN too. So they have a cloud chamber. The advantage of that one is that they've got the particle beam, so they can look at how clouds interact with cosmic rays, for example. I think there's one in Beijing, one in Japan, and one in UCLA. So they're quite rare. So there's only a handful in the world for investigating cloud processes. Ours is 10 metres high. It spans 3 floors. It's 1 metre diameter, and there's 3 cold rooms surrounding this cloud chamber. We can cool the cold rooms down to -55. So we can investigate a range of cloud processes inside this chamber. So there's different instruments that we use to measure the cloud particles too. And so here's an experiment looking at salt particles at -15 degrees Celsius. So try to explain these plots. Very similar to the cloud chamber I showed you in the first lecture. So we suck air out of the chamber, the air does work, the temperature goes down. So if you look at the temperature, if you look at the pressure, actually, this green line, pressure starts high, pressure goes down, pressure stays constant. So when the pressure starts to go down, the temperature starts to go down. So temperature going down to -23 or so here. And then when you stop lowering the pressure, it's not adiabatic, there's a heat flux from the walls which starts to increase the temperature again. And what happens when you lower the pressure, you lower the temperature, water vapour starts to condense onto the salt particles, and we measure the resulting cloud drops. So these are the size of the particles that we observe. This is against time. The colour is like the number concentration, so how many there are. So you see a cloud of cloud droplets. So cloud droplets start to grow, and then when the temperature starts to warm, those cloud droplets start to evaporate. And these are some images of the cloud droplets too. We can take images, really tiny images of these cloud droplets with a particle imager. That's called a cloud particle imager. So that's at -15. So that's showing you a supercooled cloud at -15, like the altocumulus cloud. Now these are mineral dust particles, so this shows you how different kinds of particles behave. So this is -12, so this is even warmer actually than -15. And we're doing a similar experiment, cooling the air down, air starts to warm. Now what we see with the probe that detects these particles, so we see a cloud of droplets grow, this mode here, and from that cloud of droplets we start to see ice crystals, larger particles grow. So the ice crystals are larger than the droplets. So the important thing there is we needed the liquid cloud first before we started to get the ice crystals. And you can see different shapes with the images. You see they look more angular. These are ice crystals, whereas the spherical particles that you saw on the previous slide, droplets. So it just shows you the different ways we can measure these ice nuclei. So I just want to talk through some theory now before we finish. Okay, so homogeneous nucleation first. Homogeneous nucleation of ice in supercooled water. Now this is a stochastic process. The longer you leave the drops, the more chance they have of freezing. But it depends on temperature too. And being a stochastic process, it depends on the volume of a drop, the volume of liquid water. Now it turns out one way of quantifying homogeneous nucleation is to define something called the nucleation rate, which is given a symbol J, and the nucleation rate, or the log of the nucleation rate, depends on temperature in the following way. So this is high and this is low temperature. It looks something like this. So the lower the temperature, the higher the nucleation rate. So how does that work? Now the nucleation rate turns out when you consider the statistical mechanics of it, it falls out as being a quantity that has units of number of ice germs forming per unit volume of water per second. And we can treat it as a first order rate process. So we can say that if we look at the rate of change of ice crystals, this is in the PDF of notes too, but I want to just sort of emphasize it a little bit, depends on the nucleation rate, which depends on temperature, times the volume of drops times the number of drops. That's a fairly straightforward equation. Number of unfrozen drops, volume of the unfrozen drops, and nucleation rate gives us the rate of change of ice crystals in the cloud. Now if we define the total number of particles, as being n subscript t, which equals the ice crystals n subscript I plus the droplets, So this is saying that when an unfrozen droplet freezes, it becomes an ice crystal. So the total number of particles remains constant. Then we can solve this equation, we can solve this differential equation. And it has a solution that looks like this. Number of ice crystals, a function of temperature, total number of particles into 1 minus e to j temperature. Looks something like that. And you'll have seen that, that's like the solution for radioactive decay. Yes?
Is there a reason the subscript I is different than the total?
Oh, you mean it's capital here?
Yeah, it's there.
Sorry, no, they're the same. Yeah, they should be the same. Yeah, so this subscript, n subscript little I, is the same as this subscript, n subscript big I. They're the same thing. Yeah. So it looks something like this. Time, number of ice particles. So as a function of time, number of ice particles increases if you keep the temperature constant. Whoops. So this would be total and total. Now, heterogeneous ice nuclei, heterogeneous. So, for the stochastic process, very similar to heterogeneous ice nuclei, I'm going to write down the solution. I'm going to write down the equation, sorry. Ni dNi by dtime equals, now I'm going to define this quantity omega, which is like the nucleation rate for homogeneous nucleation, but it has different units, and rather than being dependent on the volume of the drop, it's dependent on the surface area of the aerosol particle that's in contact with the drop. So we've got number of unfrozen drops, we've got the surface area in contact with these unfrozen drops, and we've got this quantity omega. So a very similar kind of equation, but omega, rather than being nucleation rate of ice in supercooled water, this is the nucleation rate of ice on a substrate or aerosol particle, solid nucleus, and it has units of number of ice germs forming per meter squared rather than per meter cubed, because this is area in contact per second. And A is the surface area of substrate in contact with drop. And what we tend to do with experiments is we try to quantify what omega is for a given type of material. Different aerosol particles all have different omega. So this is one branch of atmospheric science, is to quantify omega for atmospherically relevant aerosol particles. So they can be used to predict how ice forms in clouds. And I won't write down the solution, I'll write down the next process, which is singular. So this is an equation that describes the rate of change with temperature, because the singular process does not depend on time. Now I'm going to define this quantity K, which is dependent on temperature. Very similar to before. Now KT, it's a funny thing, KT is known as the differential nucleus spectrum. That's what you'll see referred to in the literature. All sound very complicated definitions. It's actually quite simple. It has units of number of ice germs forming per metre squared per Kelvin. So for a drop in temperature of a certain number of degrees Kelvin, it's how many ice germs would form due to that temperature drop on that material. And the relationship between K and that quantity NS, which I talked about, is just that one is the integral of the other. So if you integrate between 0 degrees Celsius and the temperature of interest, this would be the temperature of interest, the differential nucleus spectrum, then that would be how many ice germs will have become active in cooling from T0 to Tc. So if you want to say how many ice germs are present on your material, then you integrate the differential nucleus spectrum from 0 degrees Celsius down to the temperature that you're interested in. Okay. Now just to finish off, I know I'm getting towards the end here, I just wanted to say, so there's an example in the notes that asks you, it looks at homogeneous nucleation and the nucleation rate, and so it gives you J as a function of temperature. So J is a function of temperature, it's some function that you can calculate, you can evaluate, and there's a question, we say, how many drops out of 100 freeze in 10 seconds at minus 33 degrees Celsius, and the volume of the drops given 1.4 times 10 to the minus 14, so this is the typical cloud droplet, and so the answer for that, you use that exponential equation. N ice at 10 seconds is 100, 1 minus E, and you've got the nucleation rate, it's about 10 to the 6, you've got the volume of the drop, 10 to the minus 14, and you've got 10 seconds. And the answer to that is about 1 times 10 to the minus 5. So hardly any drops freeze at minus 33. And then the second part to the question is same, but at minus 38 degrees Celsius. So you calculate J minus 38. So you have to look up the definition of J. It's quite a long equation, I'm not going to define it. Works out to be about 10 to the 16. And if you substitute that in here,